Hello everyone. Welcome back to another session. And because it's Monday, we are going to go over the six problems that I have prepared. So, yes, let's start. And for those of you who couldn't join today, please watch this recording file so that uh, you guys can know the solutions to the problems. So number one is Mr. Jian is counting backward by seven, starting from 100. That is 197, 93, 86, and so on. What is his 10th number? So I saw another student solving this problem by like somewhat brute forcing. So I saw one solution that went like 100, oops, that went like 100 to 93 to 86 to 79 and so on. However, I think this is a great solution for this problem. However, I feel like when like this number changes to a bigger number. So for example, right now it is we're asked to find a 10th number, 10th term. However, what if you're asked to find like 100th term or like 1000th term? We cannot do it by hand. I mean, yes, we cannot brute force it. So we can actually write a somewhat, I'll say formula. Like we can write a function that gives us our nth term. So we know that our first term is 100. And we know that our difference is 7. Therefore, our nth term, this is nth term, or aka nth number, is equal to, as most of you might have guessed, as 100 minus 7 times n minus 1. This is n, I'll rewrite it, n minus 1. So we have, this is equal to 107 minus 7n. Then what is our 10th number? Then we know that a sub 10 is equal to 107 minus 10 times 10, 7 times 10, which is equal to 37. Do you guys understand this solution? Do you have any questions or good? Okay, thank you. Let's move on to our second question. Mm, when three positive integers a, b, and c are multiplied together, their product is 100. Suppose a is less than b is less than c. In how many ways can the number be written? So first of all, let's try and prime factorize 100. Uh, we know that 100 is equal to 2 squared times 5 squared. And we know that a, b, and c is equal to 100, where a and b and c positive, are all positive, oops, are they're all positive integers. I'll rewrite it just in case. And we know that this is true. So these are the informations that we got from, these are the information that we got from the problem, and there are no other information that the problem can give us. So, this problem, we can actually separate our cases. The first case is when a equals 1. That's when a is smallest, right? Because a, b, and c are positive integers. So our first case is a equals 1. Then we have b equals 2. Then c equals 50. When b equals 4. C equals 25. When b equals 5, then C 2, 4, 5, and C equals 20. But now we know that B cannot be equal to 10, right? Because then B and C will be the same. Then our second case is when A is equal to 2. This case, B can be equal to something greater than 2. And the smallest number that is greater than 2, but is also the factor of 100, it's 5. I mean, like 50, because we use 2. It's 5, right? So this case, C is equal to 10. But can B equal 10? Um, so we have 2, 5, and 5. The next number that we can try is 10. However, when B equals 10, then C must be equal to 5, which is not true. And our next case is, well, actually, we don't have to try from here anymore, but just to illustrate why we don't have to try, I will um continue. So our third case is when A is equal to, we did 1, we did 2, and then we have 4. Then B equals 5, and C equals 5, but it doesn't work. The next case is when A equals uh 5, but this case, B must be equal to 10, right? And from here, it doesn't work because C must be 2. And we know that the other cases will not work too. So we have 1, 2, 3, and 4. So we have our answer 4. Did everyone understand? Or do you have any other questions based on the solution? Okay, thank you. Our next problem is number 3. Because we only have 6 problems today and not many of us joined here today, I think we might end this session early if we go through all 6 problems. Number 3. How many positive integers can fill the blank in the sentence below? One positive integer is something more than twice another, and the sum of the two numbers is 28. Uh, okay, so let's say that we have positive integers a and b, and we have x right here. And without loss of generality, let's say that a is greater than b. Until here, it is all okay, right? Or do you have any question until now? Yes or no? Just in case you might wonder what without loss of generality, what it is. Without loss of generality means we are going to consider a case, but we don't have to consider the other cases because it will just be the same. So, like in this case, when we consider B is less than A, it's just the same case that we did for this one because A and B, they're not really special numbers, right? So that's why we can use without loss of generality here. They're all same cases. Um, yes, so without loss of generality, A is greater than B. Now one integer, and that is A, is X more than twice the other. And also, Wait, actually, I will just write it like this. Mm, yeah. So this is just greater, not greater than or equal to. Let's write our equation. One positive integer is x more than twice the other. So a is x more than twice the other. So this. And we know that a plus b is equal to 28. Now from here is actually quite simple. We can either brute force it or I mean we can systematically solve it by finding the minimum value and the maximum value and then just counting from there. Oh wait, actually I'll just do that. So our first case is when b equals 1. But just in case we might have like repetition, we have to be careful for that. When b equals 2, we have x equals what? 26, right? And we get 24. 3, 22, there must be 19. 4 and 24, which is 16, right? And we know that there are not much cases because we know that like 16 is not that big number and it will gradually get smaller and smaller. So we have 23, 13, 6, and 22. Wait, something's wrong here. Oh, it's 25 here. Because I was like, oh, why do you have two 22s? That does not make sense. And then the x will be, wait, it is right. It is 19. Oh, wait, maybe I just miswrote it. Yeah, like the kind of mistake that I usually mention. The next number is when x equals 10. The next case, I'll continue here. Um, no, I think I can just write it here. We have 21 and 7. And what is the next one? When it is 8, 20, and 4. Okay, so we are almost seeing the end. 9, 18. And the reason why I'm writing this is because even though, yeah, I'll explain it after finishing this. We have 19 and 1. And we should end here because it doesn't work. Okay, so, and also we know that, um, yeah, wait, but what if there is one case that we need to consider, and that is when b is a negative number. Hmm, I think there is an error in the problem. I'm sorry, but how many positive integers can fill the blank in the sentence below? One positive integer is x more than twice the other. Oh, so I think we need to assume that both a and b are positive. Otherwise, we will not get the answer. Because I was like, wait, what if b is negative? Then if b is negative, then we have so many cases. Like there are infinitely many x, and that's not what the problem maker wants. And also the problem it mentioned that we have one positive integer and it's twice the other, another. And another, it just feels like the other number is a positive number too. So uh counting, we have total of 10. Wait, did I count correctly? Oh, wait, sorry, 9. We should not include this one. The reason why I wrote all of them is because I think you guys might have been confused, if we didn't write everything. However, we don't actually have to write everything. We can just, do this one and then like try randomly this one and that one and find out that our answer is 9. But that's a quite more advanced, skill. And the reason why it's quite advanced is because we have to know that all x's are different depending on the value of b. And we can prove that because as b increase, x must decrease because if b increases, then a decreases. And also, if a decreases and b increases, then we're subtracting an increased value from the decreased value, which means x must decrease. So that's one way to think about it, but if that idea is quite hard, we can just try and write everything. And the reason why it's totally fine to try and write everything here is because we know that our initial state is not that big. But like if the problem was like the sum of two numbers is like 1009, then we do have to use the skill that I mentioned because there's too much to write everything. Good? Do you guys understand? Have any questions or okay, thank you. Let's move on to our fourth problem. How many ways can the letters in beaker, oh wait, big beekeeper, oh beekeeper be arranged so that two or more trees do not appear together? Um, I actually saw a solution from you guys. I saw a brute force sing method. And I think that is not a bad approach. Like usually when we have combinatorial problem and if we think there are not much cases, then of course we can brute force them. However, we have, I'll say, a little more systematic way or a little more smarter way of solving it instead of trying to write every single cases. And that is, let's place our E first. How many E's do you have? One, two, three, four, five. And we must have something here that is not E. Mm, And the reason why we can do that is because we know that all E's are different. So none of the E's here, they're the same. None of them are the same. And how many non-E's are there? We have one, two, three, four, five. And non-E, how many do you have? One, two, three, four, right? And they're all distinct. That's really good. So we can either place here, 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 and here. Then none of, so that two or more E's do not appear together. Then, wait, then it's actually simple. It's just 4 factorial, which is 24. Wait, oops, 24. Uh, yeah, yeah. And the reason why it's 24 is because we're just asked to find the cases of arranging non-E's. But like if like B, K, P, and R, if they were not distinct, then we should have used a different we should have divided the cases when they are the same. But because they're all distinct, we don't really have to consider the case. So we have 4 times, wait, I will just write it out. 4 times 3 times 2 times 1, which is 21. Did you guys understand? Or do you have any other questions based on this solution? Oh, okay, thank you. Then since you guys understood this problem, let me change the problem a little bit. 제가 문제를 살짝 바꿔서 um, instead of beaker, I mean, why am I keep saying beaker? It's beekeeper. Instead of beekeeper, what should I try? What should I try? Mm, okay, let's do this one, Mississippi. It's quite of a cliche, but it's a nice introductory problem. So Mississippi. Is this how I spell Mississippi? I think so. I hope so. Mississippi? No, actually not Mississippi. I don't think it's a great example here. Um, I will use A, B, actually A, B, B, A. Okay, in how many ways can this letter, be arranged so that two or more E's do not appear together? Can you guys solve this right now, really quickly? You guys can send me your answer through private chat. I will give you guys around uh 5 minutes. Uh, I don't think that's correct, Minho. Please try again. Try to use this one, and then this one. Uh, I will give you guys around 4 minutes for this problem, and then after solving it, let's all together leave the Zoom and then rejoin it. I apologize for the inconvenience. Wait, did you guys understand my solution for problem 4? Because if you guys did, it should be quite. I don't think that is correct. Please try again. Oh, wait, you didn't understand the solution. Okay. I will quickly explain it again. So, okay, so we have five E's, right? And then in order for the E's to not be like together, for the for okay, so the case in order for E to not be adjacent, we need to have a non-E alphabets in between E's, right? Did you understand until here? So we must have non-E alphabets in between E's like this, so that none of the E's are adjacent to each other. Did you understand? Okay, nice. Then we just need to consider the arrangements for B, K, P, and R here, right? Because we have B, so we can have B here, P here, K here, P here, and R here, right? But the other case is when we swap all of them. So we have, or if we switch these two, so we have R and P. So if we count all of them, how many alphabets can come in here? So we have E, here, 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 here. How many alphabets can come here? How many alphabets can be placed here? Yes, thank you, Diana. We have four. Now, how about here? How about here? We already used one alphabet here. I think it should be three here because we already used one here. So we have four alphabets, B, K, P, and R. But 우리가 여기서 하나를 사용했어요. So we use one alphabet from here. Then we have three left, right? Now, how many alphabets do we have in here? Yeah, thank you. It's two. And this one is one, right? So that's why if you multiply all of them, we get the answer 24. Did you understand? Or is it good? Okay, thank you. Then I'll give you another 3 minutes to all of you guys to solve um, the extended problem, like A, E, E, B, E, B, E, E, A. You guys are trying this one, right? Because it should be quite straightforward. Uh, I don't think they're the correct answer. 4 and 6. Um, I don't think they're correct. Please try again. If you guys think that this method is quite hard, you guys can try and brute force it because there's not many cases here. Oh, and please note that all A's, all B's, and all E's, they're same. So they're not distinct, they're indistinguishable. Okay, let's start. Because this concept is quite important. I mean, this technique is like really famous technique. So, after this, I'm going to give you one more similar problem, and maybe you guys might get it. So, okay, so this one, we have, sorry, we have four spaces for E, right? I mean, for non-E, right? So we have for E and non-E, we have 4. Now, now, how many number, I mean, how many letters can come in here to this spot? How many? How many? Yes, thank you. Now, Minha, how many alphabets can come into here, this spot? Oh, thank you. Now, wait, who? Now, Isabel, how many alphabets can come in here? Believe it should be 2, right? And the last one, it should be 1. However, here is the catch. The catch is that A, B, B, and A, B, so we have more 2 A's and 2 B's, right? So we actually have to divide it by 2 times 2. And I will show you why. Here's why. So, okay, we have A, B, B, A. Like this is my first case. And okay, let's just write it as A1, A2, and B1, B2. Our first case is this one. And now our second case is A2, B1, B2, A1. Are they the same case or not? Are they same or are they different? Are these two the same case or are they two the different case? Anyone? Are they the same or are they different? Okay, so did you guys understand until now or do you have any other questions until here? So my question is this case the same as the next case I showed you guys? Are they the same or are they different? Same, different? I need to get an answer from you guys. Actually, they are the same. So these two cases are the same. And that is because I mentioned that A sub 2, and B sub 1, B sub 2, they are indistinguishable, right? So that's why they two are the same. But we have two different arrangements for A and two different arrangements for B, right? So that's why we need to divide the whole case by the arrangements of A and B. So that's why the arrangements for A is 2, the arrangement for B is 2. So we have equals 6. Okay. Actually, I'm quite running out of time for this meeting. I have like 1 minute for this meeting. So can you guys please leave the meeting right now and then rejoin it quickly, please? I'm sorry. Okay, so the next problem that I gave you while waiting for the cooldown time for the Zoom meeting, it was how many ways are there to arrange the word me C C P? Now we're going to use the same idea from here. So what is the total number of arrangements that we can have? Like the total number. Because what is the total number of arrangements that we can have? So like the total number here I'm referring to the total number that I'm referring to here right now is where M, I, and S and P where they are all distinguishable. So they're not indistinguishable. It is actually the same idea from this problem. Do you guys know do you guys know what is this? Oh no, okay. So 5 factorial or m factorial, this means 5 times, oh yes, Isabel, do you have a question? If not, okay, so 5 factorial means 5 times 4 times 3 times 2 times 1. So a more rigorous definition would be like, and no, I'll just do this. It's not that rigorous, it's not that formal, but this is at least how they define it. But okay, okay. Um, so if 5 factorial is equal to that one, what is 4 factorial? Can you guys guess? What is 4 factorial? Oh, I will erase the rest, I think, because they're already recorded. Can you guys guess what is 4 factorial? What is 4 factorial? So like if you define 5 factorial as 5 times 4 times 3 times 2 times 1, then what is 5 factorial? I mean 4 factorial. Yes, thank you. It is 4 times 3 times 2 times 1, which is 24. And that's just like we're going to use that here. So assuming that M's, I's, and P's are indistinguishable arrangement equals how many letters are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 factorial, right? Did you guys get it? Yes or no? Do you guys understand why it is 11 factorial? Oh, okay. Thank you. Um, then, however, M, I, S, and P are indistinguishable, meaning we need to um, eliminate, I'll say, repeating part. Now, the repeating part is actually quite simple. So it will be 11 factorial over how many m's are there? 1, right? So 1 factorial. How many i's are there? 1, 2, 3, 4. So 4 factorial. How many s are there? 1, 2, 3, 4. So 4 factorial. How many p's are there? 1 and 2. So 2 factorial. And this is our answer. So that's the total number of rearrangements that we can have for Mississippi. Did you guys understand? Yes or no? Oh, okay. Thank you. Actually, there is a better way of representing this. It's just, um, This is called multinomial theorem. This is the same thing, like they're referring to the same thing, but I don't think it's quite necessary here. So yeah, just wanted to tell. Number five, it is, wait, do you guys have to like go right away after 8 p.m. or do you guys have like extra 10 more minutes? I'm sorry, because of the cooldown time for Zoom, I had to wait for 10 minutes. So are you guys available for next 10 to 15 minutes or do you guys have to go right now? Because if you guys have to go right now, I think I can sell number five and six on Thursday, but if you have more time, like 10 to 15 more minutes, then I think I can go over number five and six. So please tell me, uh, can you guys stay here a little more longer? Like 10 minutes, 15 minutes? 제가 아까 그 줌 쿨다운 타임 때문에 10분에서 10분, 15분 정도 더 지연될 것 같은데 혹시 지금 바로 가셔야 되나요, 다들? 아니면 10분에서 15분 정도 더 있으셔도 괜찮은가요? Uh, you guys can just tell me if it's fine. Okay, thank you. How about Isabel and Minha? Are you guys available? Oh, okay. Oh, okay, thank you. Okay, so I guess everyone is available. I'm so sorry for the inconvenience. And let's solve number five and six quickly together. How many ways are there to split the integers 1 through 14 into 7 pairs such that in each pair the greater number is at least 2 times the lesser number? Hmm. Uh, okay. So this problem I think is actually quite simple. Wait, what did I get for number four? I need to check my answer. Did I get 20? Yes, I did. I got 24. I think that is. And I'm sorry. And that is indeed the correct answer. Okay. Number five, sorry. How many ways are there to split into? Okay, so let's consider the pairs A, comma B, where so they're asking for the number of ways to arrange um A sub I and B sub I, the number of I'll just rewrite them. The number of A sub I, comma B sub I, where A sub I and B sub I are the elements of the set 1 through 14, and such that the greater number is at least. So wait, so this is what the problem is asking, and I just restated. Did you guys do you guys understand my restatement, or do you have any parts that you guys don't understand? Please let me know. Yeah, assuming that all of you guys understood my restatement of the problem, let's continue. Okay. Um. And also, without loss of generality, let's say that A sub I is less than B sub I. Always, without loss of generality, because the other like the opposite one, like the other one, when B sub I is greater than B sub I is smaller than A sub I, it's just the same case as when we count A sub I is smaller than B sub I. So without loss of generality, we can write this. You guys get it, right? Okay, then if we have seven, then what should be our pair here? If you have 7, then other one must be 14, right? We don't have other choice other than 14, right? We have no other choice than 14. Okay, then we have 4, 3. Oh, wait, I'm running out of space. Then we have other cases where we have 6 comma something, 5 comma something, 1 comma something, and so on. However, okay, now let's start counting here. Let's start counting. So when we have 6 here, then it is either this one, it's either 12 or 13 here, right? And 5 here is either 10, 11, 12, or 13. If it is 4, we have either 8 through 13. If you have 3, then we have 6 through 13. 2, then it is quite obvious, but 4 through 13. 1, then we have 2 through 13. Um, yes, so these are the possible cases, but notice that we have to be quite careful here. And the reason why we have to be careful here is because of these 3 cases. So we assume that 6 is going to be like 6, 4, and 2 are going to be a sub I. But in this case, it falls into the case where it is considered as b sub I. But does that work? Does that work? Does that work? So let's say we have this and this and that. Now, how about the other numbers? Obviously, this cannot be a sub I, this cannot be a sub I, no, no, and these all cannot be a sub I, right? And starting from 7, it can be. But we already have 7 numbers here. That means these cases doesn't work. 1 through 6, they always should be a sub I. So let's change these numbers. So we have 8, 8, and 8. Now let's start counting. How many possible cases do we have here? How many possible cases do we have here? In this case, how many do we have? Anyone? How many do we have here? Believe it's 2, right? Then how many cases, possible arrangements, how many cases do you have for 5? Okay, how many numbers do we have here? How many numbers do we have here? We have 4, right? We have 4 numbers, but we use 1 from here. So we have 3 left. Then how about this case? How about this case? Can anyone answer? How many cases do we have for here? 2, let's see. It's 8 through 13, so we have 8. Wait, then how many numbers are between 8 through 13? How many numbers are there? 6, thank you. But how many numbers did we use? How many numbers did we use? We use 2 numbers here, right? We use 2 and 3. That means we have 6 minus 2, which is 4. Okay, similarly, let's consider this one. How many cases do we have for here? This one, anyone? It's three, I think, because we use 여기서 하나 쓰고 그 밑에서 하나 쓰고 여기서도 하나 썼으니까 여섯 개 중에 세 개밖에 안 남았죠. 그래서 여기는 세 개가 되는 거고요. The next one here. How many do you have? How many cases do we have? We have numbers in total, but we use one, two, three, and four. That means we have two numbers left, right? And this would be obviously one. So counting all the cases, we have 2 times 3 times 4 times 3 times 2 times 1. You have 6 times 4. That's 12 times 12, which is 144. Wait, let me quickly check if I got it right, just in case. Oh, and that is indeed the correct answer. Okay, so do you guys have any questions until now, or do you understand? 이해 안 되시는 부분 있으시면 물어보셔도 괜찮습니다. You guys understand? Good or hard questions? Anyone? Okay, hard. Which part? Which part did you not get it? Okay. So if I quickly go over, then until here it is okay, right? Until here. But starting from here, uh, we know that 8, 9, 10, 11, 12, 13, and 14 cannot be A because 8 times 2 is 16, but there's no number that is greater than or equal to 16 from here. So that's why the later seven numbers must be B sub I, and the first seven number must be A sub I. Then let's list all the possible cases 1, 2, 3, 4, 5, and 6. But it's actually easier to count backwards than to count it from here because we don't know what we'll choose. We might choose 12 or 13 here, but we might not choose them. So that's why I started counting backwards because that's an easier way to count. If we choose 1 from here, where we have two cases, 12 or 13, then this case, it initially had 4. However, because we use one number from 12 or 13, we have 3 left. And similarly, we have 2, 3, 4, 3, 2, and 1. And to count the other cases, we should consider um, their arrangements. And that would simply be 2 times 3 times 4 times 3 times 2 times 1, which is 144. So that's how we get our answer. Good. Okay, let's move on to our last problem for today. Let A, M, C be non-negative integers such that A plus M plus C equals 10. What is the maximum value of that? Uh-huh. Mm, okay, so there is a thing called AMGM inequality, but we don't have to deeply study that in order to solve this problem. So 저희가 여기서 사용해야 할 정리가 하나 있는데요. It's called AMGM inequality. No, it's not like AMGM inequality. Uh, it's not AMGM inequality, but 산술기하 조합평균이라는 건데요. 이게 한국어로 해석하면 아마 산술기하 조합평균일 거예요. 근데 이 부등식을 사용해야 되는 건 아니고 이 부등식으로부터 얻을 수 있는 그 insight, understanding이 하거든요. 근데 because if I talk about this, I think it will be too long. So I'll just quickly explain what the insight is. 임의의 숫자, 뭐 A 더하기 B 더하기 C 더하기 D 더하기 쭉쭉쭉 해서 Z까지 더했을 때, no. Actually, that quite limits the cases, so I'll change it. 저희가 X sub 1, A sub 1 더하기 A sub 2 더하기 해서 A sub n까지 더할, A sub k까지, A sub n까지 더할 건데, 만약 이 값이 k래요. 4. 그러면 A sub 1 times A sub 2 times A sub 3 해서 쭉쭉쭉 A sub n까지 곱했을 때 이 값의 최대값, meaning if you want to find the maximum value of A sub 1 through A sub n all multiplied together, that is when the max is when A sub 1 equals A sub 2 equals 네. A sub 1 더하기 A sub 2 더하기 해서 A sub n까지 더했을 때 K 값이 나왔어요. 근데 저희가 이것의 최대값을 구하고 싶다. 그러면 like the maximum value of A sub 1 through A sub n all multiplied together occurs when A sub 1 through A sub n are equal to each other. 네, 이런 정의가 있어요. So 이걸 사실 사용해야 되긴 하는데, 음, 간단히 그냥 증명을 하자면, 이거 너무 길어질 것 같긴 한데, 예, 진짜 간단히 증명을 하자면, 음, A plus B, wait, should I? 네, AMGM inequality states that, 그냥, 이런 게 있구나라고만 이해하셔도 전혀 문제가 없습니다. 어, 이게 바로 AMGM inequality인데요. Like this is AMGM inequality, and the equality occurs if and only if when all the terms here are equal to each other. But we know the value of k, we want to find the maximum of this. And we already know that our left-hand side is a constant. That means, and also we know that the equality occurs if and only if all the terms are equal to each other. But the equality here is same as the greatest possible value because our left-hand side is fixed. So that's why our statement right here, that's why this is true. 근데 이게 그냥 간단한 증명이긴 한데, 굳이 여기까지는 이해 안 하셔도 돼요. 딱 이것만 아시면 바로 문제 풀 수 있으니. 자, 그러면, we know A plus M plus C equals 10. A, M, C의 최대값을 구하려면 어떻게 해야 될까요? Can anyone guess? Or do you guys know the answer to this question? When does A, M, and C achieve its maximum? 네. 사실, in order for A and C to be the greatest, A and M and C must all be equal to each other. However, notice that A, M, and C are non-negative integers. They're integers, so ideally we wanted A, M, and they want to be, ideally we want A, M, C, and C to all equal 1 over 3. However, that cannot be, 10 over 3. However, uh, this can't be true because A and C are non-negative integers. That means our closest one that we can have is 3, 3, and 4. Without loss of generality, let's say that A equals 3, M equals 3, and C equals 4. And the reason why I say without loss of generality is because our thing right here, this is, mm, wait, like this term is cyclic. This term is also cyclic. That's why. So let's calculate it. 요거랑 이거랑 같거든요. 그래서 we have 4 times 4 times 5 minus 1 times, wait, 16. AD minus 1 equals 79. Let me quickly check. Yeah, so this is the answer. I know this is quite, oh, wait. AMC? Wait, AMC? Yeah, it is right. No, sorry. My bad. I need to subtract A, M, and C. Oh, forgot about that. M minus C minus 1 equals, we have 4 times 4 times 5 minus 3 minus 3 minus 4 minus 1, which is 80 minus 6, 10, and 11, which is 69. So this is our maximum value. Sorry about the mistake. And did you guys understand the solution? I know it's quite hard, but did you guys get it? Yes or no? Ah, okay. Yes, it's okay. I chose actually, to be honest, this problem was a hard problem. It was AMC 10 problem 20. It's really hard problem. So that's why I just brought it, and it's totally fine if you guys couldn't understand this. But if you guys couldn't understand it, please review this part. I think this theorem is quite important. And yeah, so I intentionally chose a hard problem for this one. AMC 10 problem number 20 is like actually really hard problem. So it's totally fine. And yeah, so it was number 1 through 6. So homework. Number 1 is review. Number 2 is number 11 through 15 for the mock test or the AMC PDF. Good. Then thank you guys so much for coming here. These days I feel like as time pass, there are okay, so not many of you guys are actually sending your assignments, but thank you here, Mina and Diana, and also Isabel, who sent your homework, and also notified me that you guys are. So some of you here notified me that you guys can join, and some of you also notified me that you guys cannot join. For those of you who notified me, thank you so much. And yeah, this was it for today. I hope you enjoyed the 6 problems. No, actually 8 problems. Then see you tomorrow. I mean, see you on this Thursday. And yep, I hope you guys enjoyed it. Thank you, and class dismissed. Bye.
Bye.